cover today, how to do. Okay. So design for shear. Okay. So in this one, we are going to use one of the previous one of the previous problems done for moment. One of the previous one of the previous beam problems which we already designed for moment. The same thing, we are going to look at what the shear is in that particular beam and try to find the shear reinforcement for that particular beam. So that beam details are like this. Okay, so I'll probably just move a little bit ahead and show you. The clear span. The clear span was 5.7 meters. Effective depth was 410 mm. Meaning that effective span, which is equal to clear span plus effective depth, that comes to 6.1 meters. And then for that particular beam, we had calculated that the required percentage of tension reinforcement was 0.618%. I'll also show you what problem that is. Composed of 4 numbers of 16 diameter bars. The size of the beam is 300 by the effective depth is 410. Okay, 410 effective depth. Then the load I forgot to take just a minute. What is the load? Okay, this one I suppose. Okay, so this is the problem that we had already designed this particular beam. We designed it for moment. Now we are doing the same thing for shear. So initially, when we designed this for moment, we assumed some depth 350 mm, but in the end we calculated that it should be 410 mm rather. So already we calculated this as 410 mm, so we use 410 mm itself. The load, how much is the load? These are the loads. 7.5. Okay, 7.5. Live load is 7.5. Sorry, live load is 5, unfactored, and unfactored dead load is 12.5. Okay, yeah, fine. So these are the loads. Everything else is given. Okay, so the dead loads. So unfactored dead load and unfactored live load are live load is 5 and this is 12.5. Grade of steel and concrete are M25 and Fe 500. So this is the thing that is given to us. So to solve this is first thing that we need to do is, so everything else is already given. This is our clear span. Effective span we need. This is the effective span 6.1 meters. For calculating the shear strength of the concrete, we will be using what is the percentage of tension reinforcement that is used, and what is the grade of concrete that is used. Okay. So first thing, factor the dead load. Basically nothing but this into 1.5. 12.5 to 1.5 is, I think it is 18.75. And factor live load is 7.5, and the whole thing becomes okay. Now after finding the load, what did you do in designing of a beam? What is the next thing that you calculate when you design a beam? For the bending moment, what is the next thing that you calculate? after finding the load.
So we'll find the moment, sir. Moment.
Bending moment calculate. So anyway, so you'll use the formula. Now if this is a distributed load kilonewton per meter, so you will use WL square by 8 formula to find the bending moment. And all those processes have already been done in when you designed it for the moment. Now we are trying to design this for shear. So that is the thing that you have to remember. So when initially you design for moment, you design for whatever this moment was. Okay, you design for this particular moment. For designing for shear, you have to design for the maximum shear force. So how does this shear force diagram look? Simply, so this is the bending moment diagram. What is the corresponding shear force diagram? What is the corresponding shear force diagram? How does it look?
So there will be a triangle.
There will be a
triangle.
How many triangles?
Like 2 triangles, like one will be in the positive side, one will be in the negative side.
Okay, so where do they join?
Like at the mid span, like wherever the moment is maximum, the shear force will be.
Okay, so left hand side, should I draw up or should I draw it down? So this triangle, so is it a triangle like this? Is it like this? Right or wrong? Is this wrong or is this right? You said 2 triangles, they are joined at the middle. Is this right? Or this, no sir, this is wrong. 2 triangles I have, is it correct? What you said was correct. 2 triangles should be there, they will be joining at the middle. These are also 2 triangles. One is positive, one is negative.
Not like this, like at the support it will be maximum. So like it will be a perpendicular to the support and then it will be a.
Yeah. So it will be vertical at the support. So it will look like this. What is this value here and here? What is the value of this? What's the ordinate of this SFB? This is WL square by 8. What will be this?
So WL will do WL will do.
WL by 2. Okay, so your actual shear force is your maximum shear force. Okay, which is at the supports. So it doesn't matter plus or minus, magnitude wise both are same. Okay, you just need to look at the magnitude. So that is WL by 2. Okay, W is 26.25. L is 6.1 by 2. So this is the maximum shear force. Okay. Calculate it. How much?
80.062.
80.0. Okay. 06. I said 80.06. It seems very less. I hope I get a shear force which is enough to actually do design. Let me see. So I don't want this to be a case where you know what, I think I will change the load because this appears a very normal shear force. So I don't want a situation where I calculate the shear force, then I calculate the resistance of concrete and you find that you don't need to give any shear reinforcement. Then you people will get confused. So I think I will probably change the load. I'll make it a little big. But then the section will change. Okay, let's see what happens. Okay, 80.6 kilonewton. Right. So this is the maximum, but there's one condition that is given for shear force. You should take the critical section at critical section for shear at D from face of support. Okay, should be at a distance D from the face of the support. Okay, So this clear span, so our beam is like this. Okay. So if this is our beam, my effective span maybe my clear span was 5.7. Okay. This to this is 5.7. The effective depth D is 410. Okay. 410 or 0.41 meters. So from here I have to take a section which is at 0.41 meters. Right. So this is where I have to take a particular section. Okay. So basically this becomes like I have to take at, so this to this is face of the support is here. .1 meters is the effective span. Face of the support 300 mm width. So this is I'll write bigger. Okay. So 6.1 meters going on this way. Okay. 6.1 meters to that side. This whole width is 300 mm. If this is 150 mm. And here I have to take it to the section which is 410 mm. Sorry. Effective span. No? Okay. So at 6.1 meters, so we have calculated the shear force for a span of 6.1 meters. And at this 6.1 meters or at 0 meters, I have a shear force of 80.06 kilonewtons. But however, I need my shear force at a distance at a particular location which is at, so this is 6.1 minus this 150 minus 0.15 minus this D which is 410 mm. Okay, so this is 6.1 minus 0.56. How much is it? 5 point how much meters? So this was given in the question. I forgot to write it. With the support is 300 mm.
So 5.54.
5.54. Okay. So this is now easy. Either you can write the equation for shear force and calculate what is the shear force at 5.54 meters. The other simpler way to do is, since this shape is a very nice shape, it's two triangles. Okay, so it's a very convenient thing for you to just use similar triangles and find it out. Okay. So for so 6.1 means the half of this is 3.05. Okay, so 3.05 minus this. Actually, I should have done 3.05 minus 0.15. Sorry, I should have done 3.05. That makes more sense. Okay, you need to do 3.05 minus 0.15 on the 2.9. 2.9 minus 0.41. 2.49, I suppose. Okay. Okay, so I need it at 2.49 meters. So this is 80.06. How much is this? So V at D from support. V always stands for shear force. Okay, V is a common letter to use for, like M for moment, V is a common letter to use for shear force. So V at D from the face of the support, which means at 2.49 meters from the effective span location. So if it here it is 80.06, how much is it here at this point? Similar triangles. So 80.06, yeah.
65.36.
68, you are coming actually 68.
65.36.
Oh, okay, fine. There's going to end up a situation where the concrete itself can take shear. I should have used a different problem. Anyway, I don't want to confuse now. Let me complete this. So this is 65 kilonewtons. Fine. Now this 65 kilonewtons, I need to see if the given beam can take the shear. Okay. So can the given beam take the shear? Okay. So how to find it out? Pretty simple. I think I have to share my screen rather than sharing the screen itself now. So simplest thing to do is first go to, by the way, this is what I used, distance D from the face of the support for a critical section for shear. Okay. And this D from the face of the support, you are allowed to use when you have the note here. Whenever you have uniformly distributed loads, or when you have a point load which is located further than 2D from the face of the support. So whenever you have these situations, your critical section for shear, you can take a D from the face of the support. Okay, so 22.6.2, that is the relevant class. You can have a look at it. Now how to find the capacity of my beam? Go to this page ratio.
So I think your screen is not visible.
Huh?
So I think your screen is not visible. Black.
Screen is not shared.
So it's not visible.
Why? Okay. Just now I shared it. How about now? Is the screen visible now or still not visible?
No, sir, it's
Now
now it's
visible.
Not visible.
Now it's visible, sir.
Now it's visible. Okay. You are able to see the code book.
No, sir, like we can see the one note.
One note. Still one note one is coming.
Oh, yes, sir. Now your code book is visible.
Sir, I think there's a lag in the stream.
The lag. Okay, I don't want to lag. Then I'll just share the PDF itself. I don't have a confusion. One by one, I'll unshare and share. Now, PDF is visible to everyone?
Yes, sir.
Okay. Down. Okay. So this table number 19. Okay. So this will give you what is the shear strength of your concrete. It depends on the grade of concrete. It also depends on the percentage of steel that you have. Okay. So we have our details over here. Our I think now I have to move to screen. So in this problem, we have one note is visible now.
Okay.
Are you in the PDF or in the OneNote? What are you seeing now?
PDF,
So
sir.
PDF.
Still the PDF. Why is it slow? Okay. then I'll just have to do it orally for you. So I'll say, I'll just write down what you have to see. Okay, otherwise we'll just be wasting time. So now see table 19 of IS456. Okay, so from this, for PT equals 0.618%. So what is PT 0.618%? This is the one note has come or one note has not come.
Visible, sir.
Visible now, no. Okay, I'll stay at one note itself. I'll not change to anything else now. I'll just write down whatever I need. So this PT is what calculated previously when you designed for moment, and grade of concrete is M25. And we have M25. So when you go to this table 19 of IS456, you will have several list of percentage of steel and several grades of concrete. Like that, when you see, I have some value for 0.5 PT and 0.75 PT. Okay. So for 0.5, it is 0.49, 0.57. Okay. So in this table, I see 0.5 PT. I have the value of for M25, the value of tau C. This is PT. So the value of tau C is 0.49.
Sir, PDF is visible.
Oh, it got stuck in the PDF now. So now is it in PDF or is it in whiteboard?
Now okay, sir.
Okay, let me. I will not change it anymore. I'll keep it in this OneNote itself. Okay, so in this table, if anybody, sir, what I suggest is if anybody of you, all of you who are having, you should be having IS456 with you. So if possible, please open up that table and have a look. Only then you'll understand. Okay. So open table 19 of IS456. You'll be able to see these values. See, for us, our percentage of steel is 0.618, which is almost like somewhere in between 0.5 and 0.75. So I'll also say that for this particular case, my tau C, if you want, you can interpolate it. Otherwise, you just make an approximate guess of what the value will be. So my approximate guess for 0.618% of steel is halfway between this and this. So I'll write 0.53. Okay. So this is the strength of your concrete in shear. The shear strength of concrete. Now this should be more than the actual shear stress which you get. So the shear stress which you actually have will be given by what is the shear force? It's a 65 kilonewtons. So kilonewtons, so 65 into 10 power 3 divided by the effective area of concrete. Effective area of concrete is nothing but breadth of concrete, which is 300 into effective depth. Okay, not the full depth, effective depth. So that by 300 into 410. How much do you get for this? $65 divided by 340. How much is it? $65,000 by 300 into
0.528, sir.
0.528.
Yes, sir.
Oh, very close. But at least it came lesser. Okay, then I'll have to adopt something else. So this is almost 0.53 Newton per millimeter square. So it's not much more than that. It's almost exactly at whatever. This is just coincidence. Okay, that we got like this. So because of this, you can say that the beam has required shear strength. So we'll just give some nominal reinforcement. So I'm not calculating any reinforcement because it came for us. It came like tau c almost equals tau v. Okay. So I'm just saying give nominal reinforcement of. This is how you write it. Anyway, we'll do one problem to show you the actual issue. Two-legged, L means leg, two-legged 8 mm diameter stirrups at 200 is a big spacing, 200 or 220. Okay, 220 center to center. Okay. So the problem has finished with this because we got our shear strength of concrete and the actual shear stress to be almost equal. And you should not just leave it saying that okay, both are equal, so let me not give any reinforcement for shear at all. That's not a good practice. So even if it comes more, even if tau c comes more than tau v, still it's a good habit, good practice, and it's in fact a required practice to give some minimum shear reinforcement. Okay, one such minimum shear reinforcement is very typically people give two-legged. 8 mm is like a standard diameter for stirrups, 8 mm. So two-legged 8 mm stirrups at you have about 200 center to center you can give. So that will more or less take care of giving some minimum reinforcement for your shear. So the cross section of your beam would then look like this. Okay, so we had 4 mm, 16 mm bars, 4 numbers of 16 mm bars at the bottom. Now we've also given a stirrup. Okay, so to keep up your stirrups, you need to give some hanger bars. Otherwise, your stirrup will not stay. Okay. Take it on. I'll also show you SP34 for this. Okay. So this is how you have to bend it. So it's bent from here, taken around this bar, brought all the way around, comes back, and then again bent over here. Okay. So this is your stirrup. Of course, when you place your stirrups, you should make sure that the clear cover is maintained. Okay, I have drawn it very quickly, but the clear cover should be maintained. It will be a straight line. It will not be a curve. It will be all straight lines. Okay, I have shown it like some kind of a curve. That's because I didn't draw it properly. So you have the same 4 numbers of 16.5, and you'll just mark this as two-legged 8 mm bars at 220 center to center. So this is the cross section. How will it look if, and for hanger bars you can give something like 2 numbers of, this can also be 8 mm or 10 mm bars. Okay, maybe 10 mm bars you can give to just to keep it as a hanger for a stirrup. Okay, so this is how it look in the cross section. If you view it longitudinally. Okay, so viewing it longitudinally, what you'll have is you'll have, of course, you have your main bars at the bottom. Maybe half of it you will maybe you may have half of it extending beyond. Okay, like how you did in slabs. The same way you may keep some bars up top. Okay, okay. They will actually this is simply supported beam, so this is not needed. Hanger bar will be there. The 10 mm hanger bars which you kept. In case you have top reinforcement also, then you don't need a hanger bar. The top reinforcement itself will become, if you have a doubly reinforced beam, then you'll have some reinforcement here also. Okay, here you'll have some reinforcement. That itself will become a hanger bar. No need to separately give a hanger bar if you have a doubly reinforced beam. So the longitudinal bars are shown. The stirrups will be shown like this. So you just have to show it vertically. Okay. Okay, so it's you may not want to show it for the entire length of the beam. Okay, showing it one by one, all things, it's not difficult. You can just show it typically at one section and say that they are they have to be continued for the entire length or whatever. Okay, so this is your this is maybe 2 numbers of 10 bars, and these are 2 leg 8 stirrups at whatever distance that you have planned. Okay. So that's it. So here we did not actually do any calculation to arrive at this. We just took something which is a small value and gave it, because our tau v and tau c were, tau v was not too much greater than tau c. Okay. So let us take a situation where we don't have something like this. Okay. And say there's a situation where now I'm just going to assume a situation. Okay. So I'll just say assume the situation, because people should know how to calculate that reinforcement. Okay. Now let us assume that you had a beam, you did all these calculations. So a different load, different beam, similar calculations were done, similar you designed it for moment. It's safe for moment, you designed it according to what you learned, and then you are proceeding with designing for the shear. And then you are calculating the shear force, taking the critical section and seeing what the shear force is there. Say that for similar situation where your beam depth is 410, you have 0.618% of this steel PT and M25 concrete. However, you say that the loading is such that your shear force is say 100 kilonewtons. Okay. VU is 100 kilonewtons. This is an assumed situation, being done only for you to learn how to do it. Then my tau v would have become 100 into 10 power 3 by 300 into 410. How much tau v does it come now? Okay. Of course, everything is same.
.813.
How much?
0.813.
81. Okay. 0.81 Newton per mm square. Let it be 0.81 itself, no problem. Now, when you compare this tau with tau c, tau is greater. This is not good for us. Okay, means that the concrete cannot actually take all the shear that is coming on it. So this is greater than tau c. Also, you need to make another check. You also need to check table number 20. Okay, so check that in table 20. Tau v should be lesser than tau c max. So if you go to table 20, you will have several values called tau c max for different grades of concrete. And for grade M25, this is coming to be 3.1 Newton per mm square. Okay, so tau is 0.81. This is lesser than 3.1 Newton per mm square. Therefore, it's okay. Now, as a corollary, in case this was not okay, in case you had in case your tau was greater than tau c max, your only option is increase beam cross section effective area, okay, or try to increase either the breadth or the depth of the beam. There is no other option. There's nothing else you can do if your tau v was going to come greater than tau c max. Okay, whatever shear, you cannot give any number of shear reinforcement to take care of this issue. Shear reinforcement can only be given if tau v is between it's lesser than tau c max. Okay, if it's greater than tau c max, whatever shear reinforcement you give, your beam will still fail in shear compression. So the only option is you will have to increase the area of your beam if tau v becomes greater than tau c max. In that situation is not there, so we don't have to deal with that problem. Anyway, so we have tau v is 0.81 Newton per mm square. Our tau c was 0.53 Newton per mm square, meaning that my shear taken by the concrete, this is called shear resisted by concrete and longitudinal reinforcement. Okay, the component of the, so there's a total of 100 kilonewtons of shear force. How much of this 100 kilonewtons will be resisted by the concrete and the longitudinal reinforcement, that is VC, which is nothing but 0.53 into the effective area into 410 into 300. This will be in newtons. You convert it to kilonewtons. Keep it in newtons itself. We need it in newtons. How much newtons? This is 110 per 3 Newton. How much newtons is this?
$65,190.
How much?
65,190.
65,190. Oh, we had got 65 kilonewton. Okay. 65.2 kilonewton, I suppose. Okay. 65.19 or 65.2? 65.2 kilonewtons. So the shear to be taken by shear reinforcement. Shear to be taken by the shear reinforcement is nothing but given by Vs equals Vu minus Vc. So 100 minus 65.2 is about 34.8. So this much of shear has to be taken by the shear reinforcement. So what we will do is we need to use a formula for this. It is given in page number 73 of your code book. Okay. If you don't remember, in page 73 of IS 456-2000. So you have the formula VUS. This is VUS. Okay. VUS equals 0.87 FY ASVD, 0.87 FY ASV and effective depth by spacing SV. Okay. So out of this we know 0.87 FY we know, D we know, ASV which is the area of a single stirrup or shear reinforcement. SV is the spacing at which these reinforcements have to be given. Okay. So since you don't know two things, the usual thing is to assume ASV. Okay, so we'll assume the same thing, a two-legged 8 mm stirrup. We'll just change the spacing. Then ASV is nothing but what is the area of one 8 mm bar? These things you should remember without needing to calculate. What is the cross-sectional area of one 8 mm bar?
50.
50. So this is 2 leg. So this is 2 into 50. I already told you what is the meaning of leg. Okay. So VUS is 34.8. So 34.8 kilonewtons equals 0.87. Fy is 500. ASV is it's 100. D is 410. Let's find how much it should be spaced. Okay, how much is SV? Morning I had gone out now, so I shifted the class. I'm going to finish in 10 minutes. I finish it.
10 minutes left. Go back up.
I'll come in 10 minutes. Yeah. I'll come in 10 minutes. You don't chase me? How much is this?
512.5.
How much?
512.5.
512. Very high. FI, ASV. Yeah, 0.87 into yeah, 512.5. Yeah, 512.5. Yeah, it has come 512.5. Which is actually, you should not give 512.5. How much you should give is 512.5 is ridiculous. So anyway, for every problem that you have, your code book gives you a solution. So the limitations on spacing of shear reinforcement is also given to you. Where is that? It's in this. Actually, 300 is the limit, so you cannot give more than 300 in any case. Somewhere it should be mentioned. Yes. Okay. It comes 512.5 only, so that's it's a pretty low value. So you have some nice SP16 maybe. SP16. Okay. Okay, the limitation I'll tell you. There's limitation to the spacing that you give. So this comes 512.5 mm. I suppose the illumination is 300 mm. Okay, so the general typical spacing that we give is, so we'll also give for this also 8 mm bars at 220 centimeters. Whatever we gave before itself, the same to like 8 at 220. So the same can be repeated in this case also. See that what happened is, the shade which we assumed is less. It's still a bit less. It's high enough for us to require some stirrups. We still require some stirrups, but it's still not very high. It's still only about 35 kilonewtons. So when you calculate the spacing, it is coming as 512.5. 512 is not a. Or what we can do is, or you can give mild steel stirrups. Okay, you can actually think that's a good idea. You give mild steel stirrups, you get a good spacing then. So use mild steel stirrups. So when you say mild steel stirrups, it is 250 Newton per mm square yield stress. So this I think will be exactly half of this. So it will be about 256. So we should provide lesser than this. And the spacing restrictions, where is the spacing restrictions? Spacing of reinforcement. Yeah, it should not be more than 300 mm. Okay, it's written in class 26.5.1.7. It is same for everything. So your spacing restrictions for shear reinforcement is given here. So it's the limit is 300 mm as long as you do not have torsion. So because this is 256, we will give something which is lesser than this. So we can provide the same to like 8 mm mild steel stirrups at. We'll make it the same. You can keep it 250, you can keep it 220, you can keep it 200. Okay, it's up to you. Your decision. You can give any of these ranges, which is spacing is lesser than 250. And so just to repeat, so either of you, if you are wondering why I suddenly changed this from HYST 500 bar to a 250 mm bar, only for the stirrup. Okay, I did not change it for the longitudinal reinforcement. Longitudinal reinforcement is still 500. Only for stirrups alone, I decided to give mild steel bars, because if I give a 500 mm bar, 500 not mm, 500 FY bar, okay, then I got a very large spacing which is required. Okay, so it's a bit of a waste. I can still give the same 500 FY bar at 220 center to center, but it's I need not give it. Okay, so that's why I resorted to mild steel bars. But however, the main longitudinal bars are still 500 FY. Okay, the question, just a follow-up question before I end the class is, so this was our shear force diagram. Okay, our shear force diagram look like this. And we have calculated some stirrups over here based on critical section. Okay, based on the critical section. Okay, so this is the length of my beam. Critical section is somewhere, say, over here. Okay, so and similarly on this end also. Somewhere over here is the critical section, which is set to D from the face of the support. Okay, something which we did right over here. Okay, so based on the critical section, we have calculated some shear force and given the reinforcement, and that reinforcement we found as, we found it to be something which is that 2-leg setups at 800, 2-leg 8 at 220. Okay, question is, what about the remaining region? Is it necessary that I should give the same 8 mm bars at 220 center to center? Should I give the same spacing, same stirrups in the remaining part also? I'm talking about this region of shear force diagram. Should I maintain the same stirrups, or am I allowed to become? Am I allowed to increase the spacing if I want?
So since those regions come and join, so I think like we can.
Those regions will become
like joints, joints. So that if some development bar can be used, like for joint of beams or.
Joint in the sense, what joint?
Like there will be a corner, so like there will be a joint in beams. The structure.
No, which corner are you talking about? This is SFD. This is the SFD for this particular beam. Okay, so we calculated some shear force here. For this shear force, we gave this stirrup. What I'm asking is, in this region of the beam, where the shear force, see how the shear force is varying from here to here. Okay, shear force is reducing, becoming 0, and then again increasing. Okay, so compared to the shear force in this region, how is the shear force in this region? Compared to the end regions, how about the shear force in the interior of the span? How do they compare?
It's lesser.
Oh, lesser, no. So coming back to the question, so what do we do about the stirrups in this region? Should I use the same? I can use the same, but should I? If I want, I can use the same reinforcement, but should I use the same reinforcement? Is it necessary?
No, sir.
Yeah, what can you do instead? So you're allowed to increase the spacing in regions. Okay, so many times what people will do is, for some distance from the support, okay, they will give they will retain the same reinforcement, shear reinforcement as calculated for the critical. And when they come to the middle 3/4, or it's middle L by 5, yeah. So the middle, except this end L by 5 and this end L by 5. So the interior 3 by 5 length, for that region, what they will do is they will double the spacing of the stirrups. Okay. So here I cannot double. If I double it, it becomes 440. So in this region, what I can do is, instead of doubling, I'll use a different color maybe. So in the remaining region, I'll probably make it higher spacing, maybe 2-leg. If the highest spacing that I can give is 300, and I'm not allowed to give more than 300 spacing, 300 center to center. But in general, what people do is sometimes they will have a spacing like, say, for some particular problem, they may calculate a spacing like 2-leg 8 mm stirrups at 8 mm, whatever stirrups, 10 mm even. They may calculate like 100 center to center. Okay, so they will give that 100 center to center in that part where the shear is more, and for the remaining part, they will make it as 2-leg 8 mm stirrups at 200 center to center. Okay. So only thing they should ensure that wherever they start this 200, wherever they start to double the spacing, in that region, that shear force, this particular stirrups should be such that the capacity is lesser than that particular shear force. Okay, so you are allowed to, depending on, you can make your shear force calculations in this particular region and check that you're allowed to give a higher spacing. Okay, so this is these are all practical considerations. In real design, this is what they will do. They will not give the same stirrup from the end to the start. Okay, from the beginning or end to about L/5, they will give the support calculated reinforcement, and in the part between them, they will double the spacing of the stirrups, double or make it whatever spacing more. Usually, they will double it. So these are all practical things that they will do when they actually do a shear design. Okay, and finally, one thing that I don't need to solve it, but I can just show you, which is my SP16. Are you able to see this PDF SP16?
No, sir.
Why is it taking time? Okay, if it appears, just tell me. It has to appear.
Yes, sir. Yeah.
Yeah, man. Okay, fine. So those table 19, I showed you some values. No, those values are all based on. They are based on this formula. I think I showed this to you in PPT. Anyway, it's present over here. Now the formula are also present. Shear reinforcement spacing. They have given some example problems. You can go through this also. Okay, this is shear problem. This is torsion problem. We can go through this later after I finish torsion. But the main thing is, the same table 19 is reproduced here also in this page. This is page 201, and like how you find, if you remember in beam design, you went to a table, you did mu by bd square, you went to the chart for a particular grade of steel. Then for that mu by bd square, depending on the grade of concrete, you choose the percentage of steel. And similarly, you had a similar table for doubly reinforced beam also, where you get the value of PT and PC for using SP16. I hope you remember that. And here you have a similar design aid or a table for getting shear reinforcement also. Okay. So how do you use this table is first calculate the value of VUS. What is VUS? VUS is nothing but difference between the actual shear force and the shear force resisted by the concrete, the tau C into B into D which you did. So the difference, we found one difference, and for that difference only we gave the stirrups. So that difference shear force, that is VUS. Divided by D. D is the effective depth of the beam. Just keep that in kilonewton. The unit is important, kilonewton per centimeter. So find that out. Then whatever this value is VUS by D, just find that number from this table. Okay, you can just take it out from it. For example, if I get a VUS by D, kilonewton per centimeter value, if I get it to be say about 5 kilonewton per centimeter. So where do I have 5? I have 5 here. Okay, 5.694 is here, 4.881, 5. I have 5.694 over here and 4.881 over here. So that is between that I can get 5. Similarly here 5.466, 4.920. That is also close to 5. If I use mild steel bars 250. If I use 415 bars, I can take either 8 mm bars or 10 mm bars or 12 mm bars. So let me say that I want to take a 10 mm bar stirrup of Fe415 HYSD bar. Then what I'll do is I want it for 5. So let me see, this is 10 mm bars, 415 Newton per mm square. So this is VUS by D 11.342, 9.452, 8.102, 7.089, 6.302, 5.617, 5.156 and 4.726. So for 5.156, this is the closest to 5 that I have. Okay, so no need to interpolate, just choose the closest value, that's good enough. So 5.156 is the closest to 5 kilonewton per centimeter square for me. So 5.156. What is the spacing that is required? Just come all the way to this end. This is 11 centimeters or 110 mm. So for 5 kilonewton per centimeter VOS by D, I can give HYST 415 Newton per mm square bars. I can give it as I can give this two leg stirrups at 110 center to center. What's 110? It is 11 centimeters. That is what is 110. And the two leg 10 mm means, so this is the diameter of the bar that I chosen, 10 mm stirrup. And other thing is, this table is only for two leg stirrups. It's not for 3, 4, 5 or any other number of legs. This table is suitable. It's used only for two leg stirrups. But for most beams, you'll be using mostly two leg stirrups. Only for very, very big, broad, deep beams, you will have more legs in the stirrup. So for that case, you cannot use this table. You have to use the formula and find out. Okay. So anyway, we'll again be doing this when we do torsion, because torsion design is also, it is basically just flexure design plus shear design. Okay, only thing you have to change the moment and the shear according to the torsion that you have. That we will, anyway, first we will cover torsion, then we'll go to the problems. Okay, so when we do that problem, you will become more familiar with shear design and flexure design. In fact, that will complete the part of beams, which will be a big relief for me. Probably this week we can try to complete that. Finally, others can leave just 1 minute for the CR. I want to ask. Tomorrow also morning I'm not. Tomorrow morning also I'm not there. Tomorrow do you have a J slot?
So like tomorrow
Yes,
afternoon we're having, sir, like 4 to 5 we have a slot, sir.
4 to 5 is J slot.
Yes, sir.
Okay, so tomorrow also 4 to 5 we will have it.
Okay, sir.
Okay, tomorrow morning I am not there, so tomorrow morning class will not be there. Okay, instead of that only I'm taking at 4 to 5. Otherwise I will not be taking on Wednesday. Okay, only morning class will be there on Wednesday, otherwise. Okay, fine. Okay, fine. We'll end the meeting. Tomorrow evening we will meet.
Yes. Thank you, sir.
Okay. Yeah, fine. Bye.